using the Motif Finder in ProMOL. Before we go through the alignment process in ProMOL, I wanted to show you a finished product to let you know where we're headed. So what I'm showing right here is alignment between the catalytic triad and two different serine hydrolases. So they contain an aspartate, a histidine, and a serine residue, and the Motif template is shown in white and the query is shown in red. The Motif template is one of those found in the library that comes with ProMOL, and the query is the structure we enter in the search box. So we're now going to go through that process of actually starting the search. So now we're going to set up an alignment search with ProMOL. And to do that, first we're going to go to the Motif Finder tab. Let me explain the portions of this tab. On the upper left-hand corner we have the progress bars. The top progress bar represents the progress of searching one structure against the particular motif library that you've selected. The overall progress bar tells you how you're doing in terms of all the structures you've selected. So if you select 5, you can select 5 or 10 or 20 structures and run them at once. You can do that in a number of ways. You can enter a PDB entry list, so you just browse a list of PDB entries. You put one per line, no commas between lines, and you can enter that. You can actually download a list like that from the PDB if you want to. You can also search the PDB for a particular file name, but you can also come into this box and enter the PDB file name that you want to use. We have an option down here to clear the input in that box. We also have some tools here. One is a precision factor. Once you've done the alignments, you can improve the quality of alignment by varying the precision factor. You can also show the alignment between the query structure and the motif template that you've selected and the RMSD value between those two structures. And finally, on the right-hand side, we have the results window, and we'll see the results that pop up there later. Before I go any further, I want to explain how ProMOL does an alignment. What ProMOL typically does is, let's say you're starting with a serine hydrolase that contains a serine, a histidine, and an aspartate residue, and that's your motif template. So if you enter a query into ProMOL and it compares it against that particular motif template, the first thing it does is it looks for serine residues, and it flags all of the serine residues in a structure. It then looks for serine residues with a histidine residue that's within a certain distance of it. Once it gets those serine-histidine pairs in a particular structure, it does another search where it's going to look for aspartate residues that are within a certain distance of that serine-histidine pair. Once it has that, it reports out an alignment, and then you can look at that alignment in the visualization window. Now we're going to set up a search. And the query structure in this case is going to be a known serine hydrolase, 1T8L. That's the identifying, the alphanumeric ID for the structure in the protein data bank. Now I hit the Start button, and we come up with the Choose a Set window. Now here we can choose all motifs. I'm not going to do that right now. I'm going to unselect and point out that you can choose user motifs. These are the ones you've created, and the user motifs typically have a U in the name. The P set is a set of motifs that was created manually by the ProMOL team here at RIT and at Dowling College. The A set is an automatically generated set of motifs that was created in much the same way we created the P set, but it was done automatically with computer code, and so the testing was more rigorous, and the motifs typically are a little bit better, higher quality. The metal amino set is a set of motifs that contain metal ions that are bound to amino acids on proteins. The metal other set is a set of motifs that contain metal ions that are bound to non-amino acid groups, things like the heme ring, for example. It's also possible to tell ProMOL to calculate the RMSD for all alignments when you run the search, but we typically don't do this because it would do that for every alignment, and it typically doubles the time. Another possibility here is that you can limit by enzyme class, and so let's say that you knew for sure the structure you were looking for was a serine hydrolase in class 3.4, and you might enter those to limit so it didn't compare the query structure against all the other motifs in our library, just the ones that were in class 3.4. So I'm actually going to reselect the All Motifs button, and once I've selected that, it's going to compare the structure 1T8L against all motifs in the system. Then I'm going to hit the Select button to start the process. A couple things to note. We're just doing one structure here, so the top progress bar is going to be identical with the second progress bar below it. And so we're just 2% through. It's going to take 5 or 6 minutes to run this. Another thing to notice, you probably noticed that the molecular visualization window disappeared. We do that with ProMOL because it cuts down on the computational draw, the amount of computer power that ProMOL needs. If it's creating visuals as it goes along, it takes more computational power to do that. So we don't do that during the alignment process. At this point, the analysis is complete, and ProMOL was able to find 25 different results that are quite interesting, and there's a variety of things that can come of this. I want to go through the results pane and explain a little bit of what we're seeing. So we have a tree. There's actually a tool in here called Tree Widgets that helps us separate these things out. And in this tree we have, you can see as I mouse over a particular alignment, that it changes color from black to blue. Now, if you look at a particular readout, let's focus down here because these are the ones I'm going to be talking about anyway. This term 0 to 2, that's the Levenshtein distance. The Levenshtein distance is how similar the sequence that you're comparing is, or the residues you're comparing are, to the residues in the template. So if it's a value of 0, that means that it has exactly the same number of residues and identification of residues in the query structure that are found in the motif template structure. And in this case we have 0 to 2, and so it's 0 if you compare it a certain way. If you look other ways, it's possible you might actually have 2 changes between those two. The next is the name of the motif that was used for the alignment. So this is P, so this is part of the P set, and 102U is the PDB ID of the structure that was used to create that motif template, and then 3, 4, 21, 4, those are the EC numbers. So it's class 3.4.21.4. So that's a serine protease. And likewise, if we go to 1A0J here, this is an A set motif, so it was generated in automated fashion from 1A0J. And has the same exact EC class as the 102U structure does. And as I mentioned before, we compared all 6 EC classes, and when we did that, or when ProMOL ran those, what it found was that there were members from EC class number 1, number 2, number 3, and number 5, but it didn't get any alignments from class number 4 and number 6. That's a whole separate tutorial that I'm not going to go into right now. But let's take a look now at some of these EC number 3 structures. Now what I'm going to do here is first just look at 1A0J. I'm just going to double click on it, and when I double click on it, then the structure is highlighted, and it will immediately then communicate with the molecular visualization window to do the alignment. So we did an alignment with 1A0J in ProMOL. This structure, we've got some residues that are highlighted in red. We'll zoom in on those in a moment. A little hint on how to work with the program. We're also seeing the rest of the protein structure shown in cartoon format. And so what I'm going to do here is I'm going to hide the structure. So I just go on the line here that says 1T8L 1/1. Click on H for hide and hide the cartoon. Now the next thing I'm going to do is, I'm on a Mac. I'm pressing the alternate button, and I'm sliding the structure over in my view so that I can center on one particular set of residues. There's two motifs that were found there. And now I go to the display button, and I go to zoom, and I'm going to do an 8 angstrom sphere, so that makes a closer view. So what we have here then are 3 residues in the structure 1T8L that align with residues in the structure 1A0J. When I click on them, the first one, if you look in the PyMOL GUI, you'll see it listed there. It says you clicked /1T8L/C/ASP102/CB. Let me explain that. It's a structure 1T8L. We already know that. Chain C, the residue is aspartate, ASP. The residue position is 102. And the actual atom I clicked on was the beta carbon. and I just clicked on histidine 57, and then finally I'll click on serine 195. So we have those three residues. So I want to show you another trick now. If I go back into ProMOL and I click on Show Alignment and Calculate RMSD, I'm going to click on 1A0J again. And this time it does the alignment here. And what you can see is the motif is shown in white and the query is shown in red. And you can see that they lie very closely on top of each other. If we look at this, here's the aspartate, and those are almost completely superimposed. If we go to the histidine, you can see that the histidines aren't quite exactly on top of each other, but they're very close. And once again, if we go to the serine, you can see that the serine on the right-hand side here, they're also very close to each other. So this is actually a very, very good alignment. And I checked the box for Calculate RMSD. I'm not sure if you can see this well in your window, but if you go to the ProMOL graphical user interface in the top, it says 3 residues were aligned with 20 and 21 atoms. And it says then the RMSD of the alignment using all atoms equals 0.161 and so on. So this is a comparison between RMSD values for all of the atoms in all 3 side chains. The next value, it says 3 residues were aligned and 3 atoms. So this is the case where they're just aligning the alpha carbons. So in that case, the value is smaller, 0.0946, and so on. And finally, 3 residues were aligned and 6 atoms. And so that's the case where it's aligning the alpha carbon and the beta carbon for each of the 3 residues. And the Ca and Cb values, the total RMSD there is 0.1269, and so on. So here's an alignment that we obtained, RMSD values, also residues. So that's the alignment of 1T8L with the motif 1A0J. Now, just for a little bit of interest, I'm going to go to a couple different structures and see how those alignments look. So now we're doing a comparison to a structure called 1RTF. Now 1RTF is also a type of a serine protease, and this particular protease includes not only an aspartate, shown here, a histidine, a serine, but it also includes a glycine. And some of the serine protease motifs include a glycine as a certified residue in that motif. And you can see once again we get a very nice alignment here between 1T8L, which is some type of a serine hydrolase, probably a protease, and in this case 1RTF is another motif. There are a number of other serine proteases in here, including a couple of motifs that I created myself. Here's a user motif for 1A0J and a user motif for 8GCH. The U stands for user. Just for interest's sake, I'm going to click on something that isn't so closely related and see how close the alignment is. So we're now aligning with 1BVV. 1BVV is a structure, it's still an EC class 3, but it's subclass 2. And you can see in this case that we don't get a very interesting alignment. If you compare that with the quality of the previous alignments, it's not very good. Also, notice that we've just got 2 residues in the motif template, the white part. We do have 2 residues also in the query. But 2 residue alignments typically are not a very great value. One more just for fun. This is 1PGS. And here's a case, once again, it's a 2 residue alignment. And if we look at it, we've got, there is a glutamate and an aspartate. In the motif template, we have a glutamate and an aspartate. But if you look at those, the Y-shaped portion here, this is a carboxylate group, and you can see that the carboxylate groups aren't very close to each other in either alignment. And in fact, in this case, they're pointing in opposite directions. So that's probably not a very good alignment. But once again, we go back to the 1A0J, and we see this very nice tight alignment. So that tells us that this is certainly a serine hydrolase and very likely a protease. And that's the end of this, this tutorial. I'd encourage you to go out there and try this with a number of structures.